Creating an ideal calendar is impossible due to the incommensurability of our universe's main astronomical periods. The Julian calendar lagged behind real time, accumulating an error of 1 full day. The Gregorian reform by the Pope corrected this shift, excluding 10 whole days of autumn. Astronomers dream of introducing a world calendar with equal quarters and days outside weeks.
Let's talk about the calendar. It's the system that we use every single day to structure our lives. But if you ever stop to think about where it comes from, we're going to deconstruct it, really dig into the science, the history, and the incredibly tricky math problems that humanity has been trying to solve for thousands of years, all in an effort to tame time itself. So here's our roadmap for this journey. First, we'll tackle the fundamental problem, why this is so hard in the first place. Then we'll look at the two biggest attempts to solve it, the Julian and Gregorian calendars. After that, we'll get into how we even decide what year it is, and we'll finish up by looking at the ongoing quest for the perfect calendar. Okay, let's dive right into the core challenge. The heart of the problem is that the universe just doesn't operate on a tidy schedule. The way the Earth spins, the Moon orbits the Earth, and the Earth orbits the Sun, well, their cycles just don't line up neatly. From a timekeeping point of view, nature is actually pretty inconvenient.
So what is a calendar, really? At its core, it's just a tool we invented to count long stretches of time, and its main job is to try and sync up our human activities with three giant cosmic clocks: the day, which is the Earth spinning, the month, which is the Moon circling us, and the year, which is us going all the way around the Sun. Now, let's look at the first critical number. This is the big one, the tropical year. That's the time it takes for the seasons to make one full cycle, say from the first day of spring back to the first day of spring. And here's the kicker. It's not a nice round 365 days. Nope, it's 365.242186 days. And that little fractional part, that 0.24 something, that's where all the trouble begins.
All right, on to our second critical number. This one's all about the moon. A synodic month is the time it takes to go from one new moon to the next. And surprise, surprise, this number isn't clean either. It's about 29.5 days. And just to make things extra difficult, that number doesn't divide evenly into the year. It's a real mathematical headache.
So what this means is that these three fundamental cycles, day, month, and year, are mathematically incommensurable. They just don't fit together perfectly. The best way to visualize this is to imagine three huge cosmic gears. You've got a small gear for the day, a bigger one for the month, and a giant one for the year. They're all turning together, but because their sizes aren't perfect multiples of each other, their teeth never ever line up perfectly again. Any calendar we create has to decide which of these gears it wants to follow most closely.
So humanity is facing this messy, unsolvable cosmic puzzle. What was the first really serious, systematic attempt to fix it? Well, that brings us to the Roman Empire and the famous Julian calendar. For its time, it was a brilliant and practical solution. The year is 46 BC. The man of the hour is Julius Caesar. The calendars across the Roman world are a complete mess, so he consults with an expert astronomer, Sojournes of Alexandria, and tasks him with creating one stable, predictable calendar for the entire empire, based on the sun.
And the system they came up with was, you have to admit, beautifully simple. Here's how it worked. You have 3 regular years with 365 days. Then on the 4th year, boom, you add an extra day to make a 366-day leap year. This extra day was slipped in after February 23rd, which, due to some Roman naming conventions, ended up giving us the term bissextile for a leap year. But, and there's always a but in this story, here's where a tiny little flaw crept in. By adding one day every 4 years, the Julian calendar's average year is exactly 365.25 days, or 365.25. But remember that actual physical number for the tropical year? It's 365.2422. The Julian year was just a tiny bit too long.
Now you might be thinking, that difference is minuscule. Who cares? Well, the problem is it adds up. Think of it like a watch that runs just a few seconds fast every day. It's not a big deal at first, but over months and years, it becomes a real problem. This tiny error meant the Julian calendar drifted away from the actual seasons by 1 full day every 128 years. Okay, let's fast forward about 16 centuries. By the late 1500s, that tiny error wasn't so tiny anymore. It had accumulated for so long that the calendar was now seriously out of whack with the seasons. This became a huge problem, especially for the church, and it set the stage for the next great leap in timekeeping, the Gregorian reform. So what was the final straw? It was actually all about calculating the date of Easter. Way back in 325 AD, the Council of Nicaea had locked in the first day of spring, the vernal equinox, as March 21st. But because of that slow Julian drift, by 1582, the real first day of spring was happening on March 11th. The calendar was off by 10 whole days. So how do you fix a 10-day error? You have to do something dramatic. Pope Gregory XIII basically hit the fast-forward button on history. He issued a decree that the day after Thursday, October 4th, 1582, would not be October 5th. No, it would be Friday, October 15th. Just like that, 10 days were literally deleted from the calendar. Imagine going to bed one night and waking up 10 days in the future. Okay, so they'd reset the clock, but how did they stop it from drifting again? They came up with a much smarter, more sophisticated leap year rule. The basic rule is the same, a leap year every 4 years. But here's the first exception. Century years, like 1700, 1800, 1900, are not leap years. Then there's an exception to the exception. If that century year can be divided by 400, like the year 2000, it is a leap year after all. It's a much, much finer adjustment. And what was the result of this clever new rule? A massive, massive jump in accuracy. Remember, the Julian calendar was off by a day every 128 years. The new Gregorian calendar? It takes about 3,300 years to be off by that same single day. Now that is a serious upgrade. All right, so we've pretty much solved the problem of making the year line up with the seasons. But there's a whole other piece to this puzzle. What year is it? I mean, how do we even number them? This isn't really a physics problem anymore. It's a question of human convention.
This whole idea of counting years from a specific starting point is called an era. And the one most of the world uses today, the whole Anno Domini or AD system, was actually proposed by a monk named Dionysius back in the 6th century. He just picked a starting point, and for various historical reasons, it stuck. But from a scientific standpoint, that starting line is completely arbitrary.
Now, this convention leads to a really strange mathematical quirk that trips a lot of people up. You know how the years go, 2 BC, then 1 BC, and then what comes next? Logically, you'd think year 0, right? Nope, it jumps straight to 1 AD. There is no year 0 in the standard system. It's like a missing step on a staircase right at the most important part.
As you can imagine, this missing year 0 is a huge headache for astronomers who need to do calculations across thousands of years. So they came up with their own, more logical system. For them, the year we call 1 BC is simply year 0. Then 2 BC is year -1. 3 BC is year -2, and so on. It creates a seamless, continuous number line that actually works for doing math. So the Gregorian calendar is incredibly accurate when it comes to tracking the seasons. But is it perfect? Not by a long shot. It actually has some significant structural flaws, which brings us to our final section, the ongoing intellectual search for an ideal calendar. The problems aren't about physics anymore. They're about organization and just plain convenience. I mean, think about it. Why do months have 28, 29, 30, or 31 days? It's kind of a mess. That means the quarters of the year are unequal lengths, which is a pain for business. And probably the biggest annoyance is that the calendar isn't perpetual. Your birthday, for example, falls on a different day of the week every year. The whole grid shifts around.
So naturally, people have tried to design a better, more logical calendar. One of the most well-known proposals is called the world calendar. It's built for consistency. The year is divided into 4 identical 91-day quarters. Each quarter has exactly 13 weeks and always starts on a Sunday. But wait, 4 times 91 is only 364. So what about day 365? They cleverly make it an extra day, a world's day. That's a holiday and doesn't belong to any week. That way, the calendar is exactly the same year after year.
And this really leaves us with one final big question. Our current Gregorian calendar, for all its quirks, is accurate enough and it works. We're all used to it. So is the pursuit of a perfectly logical perpetual calendar a truly necessary scientific goal that we should be striving for, or is it just a fascinating but ultimately academic puzzle for thinkers to try and solve? That's something we're thinking about.
Thank you, friends. Strive for understanding and become wiser. See you soon.